8, 7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
Houston is now controlling.
On the night of April 14th, 1970, 3 men sat inside a crippled spacecraft approximately 171 kilometers from Earth. They were farther from their home planet than any human beings had ever been or have been since. The Apollo 13 mission, crippled by an oxygen tank explosion that forced its crew to abandon the command module and shelter in the lunar module, swung around the far side of the moon on a free return trajectory that carried it to a distance that still stands as the outer boundary of human physical presence in the universe. James Lovell, Jack Swigert, and Fred Haise were not there by choice. The trajectory was dictated by the physics of their emergency, and the distance they reached was incidental to their survival. Yet that number, 400,171 kilometers, remains the definitive answer to the simplest version of the question of how far humans have traveled in space. Every other discussion of limits, whether near-term or theoretical, begins from the acknowledgment that this record has stood for over half a century, and that the boundary it represents is not merely a reflection of technological capability, but of the profound difficulty of sustaining human life beyond the protective cocoon of Earth's gravity, atmosphere, and magnetic field. The Moon itself, the target of all crewed missions that have ventured beyond low Earth orbit, lies on average about 384,400 kilometers from Earth. This distance varies because the Moon's orbit is elliptical, ranging from roughly 356,000 kilometers at perigee to about 406,700 kilometers at apogee. 12 human beings have walked on the lunar surface, all between 1969 and 1972, and none since. The technology that carried them there, the Saturn V rocket and the Apollo spacecraft, represented the pinnacle of 1960s engineering, a system developed under the pressure of geopolitical competition and abandoned when that pressure subsided. The distance the Moon represents is not merely a physical measurement. It is a statement about the conditions under which humanity is willing to invest the resources and accept the risks required to send people beyond the familiar. Low Earth orbit, where the International Space Station and all crewed missions since Apollo have operated, lies between roughly 400 and 420 kilometers above Earth's surface. From the perspective of cosmic distances, this is negligible. The ISS orbits at a height roughly equivalent to the distance between 2 neighboring cities. Yet this modest altitude places astronauts outside Earth's atmosphere, where they are exposed to elevated levels of radiation, experience microgravity's physiological effects, and must rely entirely on engineered systems for every breath and every sip of water. The contrast between the intimacy of low Earth orbit and the vast distances of even nearby space illustrates the fundamental challenge. Space is not merely empty. It is actively hostile to biological life, and the difficulty of sustaining that life grows with every additional kilometer of distance from Earth. The history of human spaceflight has followed a trajectory that began with breathtaking ambition and then contracted. The 1960s saw rapid escalation, from Yuri Gagarin's single orbit in 1961 to Neil Armstrong's footprint on the Moon in 1969, a span of only 8 years. The Apollo program pushed human beings to their farthest point and then retreated. Subsequent decades focused on low Earth orbit, developing space stations and shuttle systems, accumulating knowledge about long-duration spaceflight, and building the infrastructure of routine access to near-Earth space. The boundary established by Apollo 13 was not extended because the next logical destination, Mars, required capabilities that exceeded what any nation was willing to develop in the absence of a driving imperative comparable to the Cold War space race. This history matters because it establishes that the limits of human space travel are not purely technological. They are also political, economic, and biological. Technology has advanced enormously since 1972. Computers, materials, propulsion systems, and life support have all improved dramatically. Yet humans have not returned to the moon until very recently, with NASA's Artemis program aiming to restore a lunar presence in the mid-2020s. The gap between what is technically possible and what is actually achieved reflects the weight of competing priorities, the cost of spaceflight, and the difficulty of sustaining political will across the decades required for ambitious programs. The biological limits deserve particular emphasis because they are less negotiable than political or economic ones. Human bodies evolved in a specific environment, at a specific gravity, within a specific magnetic and atmospheric shield. Removing people from that environment initiates a cascade of physiological changes. Muscles atrophy in microgravity because they no longer need to support body weight. Bones lose density as mechanical loading decreases. Fluids shift toward the head, causing vision problems that have affected a significant fraction of ISS astronauts. The immune system is altered. Sleep is disrupted by light cycles and stress. Radiation exposure increases with duration and distance from Earth, accumulating damage to DNA that manifests as elevated cancer risk over a lifetime. These effects are manageable on missions of days or weeks. Over months, they become significant but still reversible with rehabilitation after return. Over years, the picture becomes more uncertain. The longest continuous human spaceflight, Valery Polyakov's 437-day mission, aboard Mir in 1994 and 1995, demonstrated that extended missions were survivable, but extracted physiological costs that required months of recovery. Scott Kelly's year-long ISS mission, which included his twin brother Mark as a ground control subject, provided detailed data on how human physiology responds to a year in space. The results were instructive. Some changes were temporary. Others, particularly in gene expression and some aspects of cognition, were more persistent. For missions beyond Earth orbit, particularly to Mars or more distant destinations, the radiation environment changes dramatically. Within Earth's magnetosphere, astronauts are partly shielded from galactic cosmic rays and solar particle events. Beyond the magnetosphere, this protection disappears. Astronauts traveling to the Moon during Apollo missions were exposed to higher radiation levels than ISS crews, though the short duration of lunar missions limited total doses. For a Mars mission lasting 18 to 24 months round trip, radiation exposure would significantly exceed recommended lifetime limits under current standards. For destinations farther than Mars, the exposure would be proportionally greater. What the boundary we have already reached reveals is that the question of how far humans can travel in space has two distinct components. The first is engineering. What technology permits in terms of velocity, life support, and mission duration. The second is biology. What the human body can tolerate in terms of radiation, microgravity, psychological isolation, and physiological stress. These two components interact. A faster spacecraft reaches its destination sooner, reducing radiation exposure. A more capable life support system extends mission duration without proportional biological cost. But neither component can be fully decoupled from the other, and both impose limits that do not yield easily to incremental improvement. The boundary established by Apollo 13 is a starting point. Understanding where the limits truly lie requires examining each layer of constraint in turn, from the nearest planetary destinations to the absolute walls imposed by physics itself. The Moon is not simply the farthest place humans have been. It is a threshold, a first demonstration of what leaving Earth's immediate vicinity requires and what it costs. The lessons learned from the 6 successful Apollo landings and the near disaster of Apollo 13 shaped every subsequent assessment of human spaceflight beyond Earth orbit. Those lessons were not primarily about propulsion or navigation, though both were essential. They were about the depth and complexity of the challenge of sustaining human life in a truly alien environment, even one as close as the Moon, and about the cascade of problems that emerge when systems fail, far from any possibility of rescue. The Moon's surface environment is extreme in ways that Earth observation does not fully convey. There is no atmosphere, which means no protection from solar ultraviolet radiation, no thermal buffering to moderate temperature swings, and no medium for sound. Temperatures on the lunar surface range from approximately 130 degrees Celsius during the 2-week lunar day to minus 180 degrees Celsius during the equally long lunar night. The regolith, the layer of fragmented rock and dust covering the surface, is abrasive and electrostatically charged, clinging to everything and potentially damaging equipment and lungs if inhaled. Dust contamination was a persistent problem during Apollo missions. Astronauts found their suits and equipment coated with fine particles after only a few hours of surface activity, and the long-term effects of lunar dust inhalation on human health were a genuine concern. Microgravity during the transit to and from the Moon, along with the Moon's surface gravity of approximately 1/6 Earth's, created physiological challenges that the short duration of Apollo missions largely masked. The longest any Apollo crew spent on the lunar surface was about 75 hours during Apollo 17. This was too brief for the most serious effects of reduced gravity to manifest, but subsequent analysis and the experience of long-duration ISS missions made clear that extended stays on the Moon would require addressing bone loss, muscle atrophy, and cardiovascular deconditioning in a gravity environment insufficient to fully prevent these effects. Radiation was another concern that Apollo missions encountered but did not fully resolve. During the Apollo 16 mission, a solar particle event produced elevated radiation levels, though it did not rise to a level that incapacitated the crew. The timing was fortunate. A major solar storm during a lunar transit, with astronauts outside Earth's magnetosphere and without adequate shielding, could deliver a lethal dose. The unpredictability of solar particle events makes radiation one of the most difficult hazards to manage for missions beyond low Earth orbit. The Apollo program addressed this primarily through acceptance of risk rather than comprehensive mitigation, a strategy that reflected the extraordinary pressure of the lunar program's timeline. The psychological dimensions of lunar missions were explored but not fully understood during Apollo. The crews were small, 3 people during transit and 2 on the surface. Missions were short enough that isolation did not have time to produce serious psychological effects. Communication with Earth was possible in real time, with only a 1.3-second signal delay for Moon-to-Earth round trips. Yet astronauts reported the profound experience of seeing Earth as a small, fragile sphere against the blackness of space, and of standing on a world where every human who had ever lived existed as a single, distant point of blue light. These experiences were psychologically significant, and their long-term effects on astronaut mental health and worldview became a subject of study in subsequent decades. The Apollo program also revealed the limitations of chemical propulsion for sustained human exploration beyond Earth. The Saturn V, the most powerful rocket ever flown, could place approximately 130 metric tons into low Earth orbit and send roughly 47 metric tons toward the Moon. Its propellant, liquid oxygen and liquid hydrogen, produced the highest specific impulse achievable through chemical combustion, yet the rocket itself stood 111 meters tall and weighed nearly 3,000 metric tons fully fueled. The vast majority of that mass was propellant consumed in the first few minutes of flight, leaving only a small fraction to actually reach the Moon. This ratio, a consequence of the rocket equation, illustrated the fundamental inefficiency of chemical propulsion for deep space missions. Every additional kilogram of payload required multiple additional kilograms of propellant, which in turn required more propellant to accelerate in a compounding spiral. Despite these challenges, the Apollo missions established a critical precedent. Humans could survive and work in deep space, at least for short periods. They could navigate to another world, land, conduct scientific work, and return. The systems required to do so were complex and expensive, but they were buildable. The knowledge gained from Apollo about life support, thermal management, navigation, and human physiology in space formed the foundation for every subsequent crewed mission design. The decades following Apollo saw a deliberate retreat from deep space exploration, a focusing of human spaceflight on low Earth orbit. The Space Shuttle, which flew from 1981 to 2011, was designed for orbital operations and never ventured beyond a few hundred kilometers altitude. Mir, the Soviet and later Russian space station, accumulated years of human presence in space, but at altitudes well within Earth's magnetosphere. The ISS, operational since 2000, has hosted over 200 astronauts and cosmonauts from 19 countries, providing an extraordinary database of human physiological response to long-duration spaceflight in low Earth orbit. That database revealed both encouraging and concerning findings. On the encouraging side, humans can survive and function in space for up to a year with appropriate countermeasures. Regular exercise mitigates but does not eliminate bone and muscle loss. Pharmaceutical interventions and dietary modifications help manage specific physiological changes. Communication technology, while subject to increasing delays at greater distances, can maintain psychological connection to Earth and support teams. On the concerning side, some physiological changes do not fully reverse after return to Earth. Visual impairment associated with increased intracranial pressure, observed in a significant fraction of long-duration ISS crew members, has no fully effective countermeasure. The mechanisms are not completely understood. Cognitive changes detected through neuroimaging and psychological testing in some astronauts after long-duration missions raise questions about cumulative effects on the brain, and all of these observations were made in the relatively protective environment of low Earth orbit. At greater distances, radiation exposure increases, and the ability to return home quickly in a medical emergency disappears. The Moon, as humanity's farthest destination and the site of its only crewed landings beyond Earth orbit, sits at the threshold between what has been demonstrated and what remains to be proved. Returning to the Moon, as NASA's Artemis program intends, will test whether the lessons of Apollo can be applied to build a sustainable presence rather than a series of brief expeditions. The challenges of extended lunar habitation, managing dust, radiation, psychological isolation, resupply logistics, and medical emergencies far from Earth will provide essential experience for the far more demanding journey to Mars. What the Moon as a threshold taught humanity was that the boundary of human spaceflight was not merely technical, but systemic. Every component of a crewed mission, propulsion, life support, navigation, communication, medical care, psychological support, had to work together with extraordinary reliability in an environment that offered no margin for failure. The complexity of that system and the resources required to build and operate it explained why the boundary had not been extended in half a century. Extending it to Mars and beyond would require not just better technology, but a sustained commitment of resources and institutional capacity that exceeded any previous space endeavor. The Moon was close enough to be a first step. Everything beyond it required a qualitative change in what humanity was prepared to undertake. Mars is the next plausible destination for human spaceflight, and it represents a boundary of a qualitatively different kind from the Moon. The red planet is not merely farther away in distance. It is separated by a gulf of time, risk, and logistical complexity that transforms every aspect of mission design. The Moon lies a few days' journey from Earth, close enough that resupply and emergency return, while difficult, are conceivable. Mars, at its closest approach, lies about 54 million kilometers away, a distance that light takes 3 minutes to cross. At its farthest, it is over 400 million kilometers distant. A one-way journey using current or near-term propulsion takes between 6 and 9 months, depending on the trajectory chosen. A round trip, accounting for the wait period on Mars while the planets realign for the return journey, spans 18 to 24 months. During the entire mission, real-time communication with Earth is impossible. Signal delays range from 3 to 22 minutes one way. Every decision, every emergency, every system failure must be handled by the crew with information that is minutes to tens of minutes out of date. This communication delay is not a minor inconvenience. It fundamentally changes the nature of human spaceflight. All crewed missions to date have operated in near real-time contact with Earth-based mission control, where teams of specialists monitor systems, analyze anomalies, and provide guidance within seconds or minutes. For a Mars crew, Earth's expertise is effectively unavailable in any urgent situation. A medical emergency, a life support failure, a navigation problem, all must be resolved by the crew using onboard resources and pre-planned procedures. This imposes requirements for crew competence, onboard medical capability, and autonomous system management that far exceed anything previously demonstrated. The distance also makes emergency return impossible. An Apollo crew facing a crisis could abort and return to Earth within days. A Mars crew has no such option. Once committed to the surface, they must remain for months until the planetary alignment permits departure. If a crew member suffers a severe injury, illness, or psychological breakdown, the mission must continue despite the incapacitation. This reality requires not only advanced onboard medical systems, but a careful selection and psychological screening process for crew members, along with social and organizational structures that can maintain cohesion under extreme stress over periods of nearly 2 years. The physiological challenges of a Mars mission compound those of the transit in both directions. After 6 to 9 months in microgravity, a crew arriving at Mars would be deconditioned, their bones and muscles weakened, their cardiovascular systems adapted to the reduced demands of weightlessness. They would then need to function on a planet with 38% of Earth's gravity, wearing spacesuits in an environment where the thin carbon dioxide atmosphere provides no breathable air, and surface pressure is less than 1% of Earth's. The combination of physiological deconditioning and immediate operational demands upon arrival creates a scenario with no parallel in the history of crewed spaceflight. Mars's radiation environment adds another layer of concern. Unlike the Moon, which can at least offer some shielding through the use of subsurface habitats or regolith berms, Mars provides minimal atmospheric protection. The thin Martian atmosphere, equivalent to about 1% of Earth's, attenuates some radiation but provides far less shielding than Earth's atmosphere. Galactic cosmic rays penetrate the surface, exposing crew members to elevated doses regardless of whether they are outdoors or inside surface habitats. Estimates suggest that a Mars mission crew would receive radiation doses significantly exceeding current NASA lifetime limits, increasing cancer risk by several % or more, depending on the duration of the mission and the solar activity during transit. Mitigation strategies exist but are imperfect. Habitats with thick walls of regolith or water provide shielding, and crew members could retreat to a more heavily shielded area during solar particle events. Pharmacological interventions, such as radioprotective drugs, are being studied and show some promise. Advanced warning systems for solar events, combined with rapid shelter protocols, can reduce peak doses. But galactic cosmic rays, whose energies are far higher and whose flux is continuous, cannot be fully blocked by any practical amount of passive shielding. The radiation problem for a Mars mission does not have a fully satisfactory engineering solution, only a series of partial mitigations that reduce risk without eliminating it. Life support for a Mars surface mission presents challenges that extend well beyond the transit. A Mars habitat must provide breathable air, water, food, temperature control, and waste management for a crew of 4 to 8 people for at least 18 months. The water and air components can be substantially recycled, as demonstrated on the ISS, but no system is 100% efficient. Losses must be made up from stored supplies or from local resources. Mars has water ice at its poles and possibly in the subsurface, but extracting and processing it for human use requires infrastructure that must either be brought from Earth or manufactured on Mars using local materials. The concept of in situ resource utilization, using Martian materials to produce propellant, water, oxygen, and construction materials, is central to most serious Mars mission architectures. The Martian atmosphere is primarily carbon dioxide, which can be converted to oxygen and carbon monoxide through electrolysis. Water, combined with carbon dioxide, can produce methane and oxygen, which can serve as rocket propellant for the return journey. NASA's MOXIE experiment, flown on the Perseverance rover, demonstrated small-scale oxygen production from the Martian atmosphere, validating the concept in principle. But scaling these processes to the level needed for a crewed mission requires infrastructure of a complexity and mass that has never been deployed to another planet. The entry, descent, and landing problem for large payloads on Mars is another unresolved challenge. Mars's thin atmosphere provides insufficient drag for aerobraking alone, and the planet's surface gravity is sufficient to make powered landing fuel-intensive. Current robotic landers manage masses of up to about 1 metric ton on the Martian surface. Crewed missions would require landing tens of metric tons of habitat, life support, and surface equipment, an increase of 2 orders of magnitude that requires either a fundamentally different landing system or the prior deployment of surface infrastructure by robotic precursor missions. Despite all of these challenges, Mars is considered the only realistic, near-term destination for human spaceflight beyond the Moon. It has a surface on which humans can stand, a day length similar to Earth's, water ice for potential use, and enough resources to support in-situ production of propellant and life support consumables. It lies within the range of current or near-term propulsion technology, and its study by robotic missions has provided enough data to plan a crewed expedition with reasonable confidence in what conditions crews would encounter. The trajectory toward a crewed Mars mission has accelerated in recent years. NASA's Artemis program, while focused on the Moon, is explicitly framed as a stepping stone to Mars. SpaceX has developed the Starship system, designed with Mars colonization as its stated purpose, and capable in principle of delivering very large payloads to the Martian surface if technical challenges are resolved. China has announced intentions to send crewed missions to Mars in the 2030s. The geopolitical dynamics that drove Apollo to the Moon are re-emerging in a new form, suggesting that political will may eventually align with technical readiness to make a Mars mission real. Mars, therefore, represents the edge of what is practically reachable within the coming decades, the point where engineering challenges and biological constraints intersect with political and economic realities to define the near-term boundary of human space travel. It is not the farthest humans could theoretically go, even with current technology, but it is the farthest destination for which a credible path exists, and reaching it would constitute the most significant expansion of the human boundary in space since Apollo 13 swung around the Moon in 1970. Beyond Mars lies a vast region of the solar system that has been explored extensively by robotic spacecraft, but never by human beings. The asteroid belt, Jupiter and its moons, Saturn and its rings, Uranus, Neptune, and the distant realm of the Kuiper belt and Oort cloud collectively span an enormous volume, from roughly 2 astronomical units to perhaps 100,000 astronomical units from the Sun. The bodies within this region range from minor asteroids a few meters across to gas giants with dozens of moons, some of which harbor conditions considered potentially hospitable to life. The scientific and strategic value of exploring these regions with human presence is widely recognized, yet they lie far beyond the boundary of what is achievable with chemical propulsion within any time frame that can be considered practical for crewed missions. Chemical propulsion, the technology that has powered every crewed spacecraft in history, operates by expelling propellant at high velocity through a nozzle, generating thrust through Newton's third law. The efficiency of a rocket engine is measured by its specific impulse, roughly the thrust produced per unit of propellant consumed per second. The most efficient chemical propellants, liquid oxygen and liquid hydrogen, achieve specific impulses around 450 seconds. A value that represents the practical ceiling of chemical combustion. This specific impulse, while sufficient for reaching Earth orbit and the Moon, becomes inadequate for missions to the outer solar system on timescales compatible with human life. The challenge is transit time. Jupiter lies between 4.2 and 6.2 astronomical units from Earth. Depending on orbital configuration, a distance of roughly 600 to 900 million kilometers. The Voyager 1 spacecraft, launched in 1977, reached Jupiter in about 18 months using a high-energy trajectory and a gravitational assist from Jupiter itself. A crewed mission to Jupiter could not use a simple flyby trajectory. It would need to carry fuel for deceleration and return, dramatically increasing the required propellant mass. Even an optimized trajectory using gravitational assists might take 2 to 3 years one way. 18 months to 3 years in interplanetary space, exposed to galactic cosmic rays without the partial shielding of Earth's magnetosphere, would expose crew members to radiation doses that far exceeded any level considered safe. The psychological and physiological effects of such a journey, in the isolation of a spacecraft with no resupply and no possibility of emergency return, would be more severe than anything encountered on a Mars mission. The onboard life support system would need to function reliably for 4 to 6 years round trip, a requirement that pushes closed-loop ecological systems far beyond any demonstrated capability. Saturn, Uranus, and Neptune lie at 9, 19, and 30 astronomical units respectively. Travel times with any propulsion system based on currently demonstrated technology scale with distance in ways that make crewed missions to these destinations effectively impossible on human timescales. Voyager 2, which flew past all 4 outer planets, took 12 years to reach Neptune, using gravitational assists at each planetary flyby. A crewed mission to Neptune, even with theoretical near-term nuclear thermal propulsion, might take 5 to 10 years one way. No life support system, no radiation shielding strategy, and no psychological model has been developed that could support a human crew for such a mission. Nuclear thermal propulsion offers meaningful improvement over chemical systems. These engines use a nuclear reactor to heat propellant, typically hydrogen, to very high temperatures before expelling it through a nozzle. The resulting specific impulse, approximately 800 to 900 seconds, is roughly twice that of the best chemical engines. This does not sound like a dramatic improvement, but in the context of the rocket equation, it reduces the propellant mass required for a given mission significantly. For a crewed Mars mission, nuclear thermal propulsion could reduce transit times to roughly 4 months, compared to 6 to 9 months with chemical propulsion. For outer solar system missions, it would enable transit times that remain years long but become marginally more feasible. Nuclear pulse propulsion, the concept explored in Project Orion in the late 1950s and early 1960s, involved propelling a spacecraft by detonating a series of nuclear bombs behind a pusher plate. Theoretical specific impulses in the range of 10,000 seconds or higher were projected, enabling transit times to Jupiter of months rather than years. The concept was technically sound within the bounds of known physics, but it was abandoned due to the treaty prohibiting nuclear weapons testing in space and concerns about radioactive fallout during atmospheric launches. Reviving it would require not just technical development, but resolution of significant political and environmental issues. Electric propulsion systems, which use electromagnetic fields to accelerate ions or plasma, achieve very high specific impulses, sometimes exceeding 10,000 seconds, but at very low thrust levels. This combination makes them ideal for slowly accelerating robotic spacecraft over months or years, but impractical for crewed missions that require rapid acceleration to minimize transit times and radiation exposure. A hybrid approach, using electric propulsion for sustained low-thrust acceleration over months combined with a nuclear power source, could theoretically achieve higher velocities than chemical rockets, but the timescales involved remain challenging for crewed missions beyond Jupiter. Nuclear fusion propulsion, if ever achieved, would represent a step change in capability. Fusion reactions release energy several orders of magnitude greater than chemical combustion per unit mass of fuel. Specific impulses in the range of 10,000 to 100,000 seconds might be achievable with fusion-powered engines. Transit times to Jupiter could drop to weeks, and missions to the outer solar system could take months rather than years. This would bring much of the solar system within reach of crewed missions of manageable duration. However, controlled nuclear fusion for energy production remains undemonstrated at the scale needed for propulsion. Despite decades of research and enormous investment, no fusion reactor has yet achieved net energy gain, the condition where more energy comes out than is put in. The National Ignition Facility achieved this milestone in 2022 for a brief moment in a specific configuration. But scaling from laboratory demonstrations to a fusion rocket engine involves challenges that are not yet clearly mapped. The transition from a physics demonstration to an engineering product typically takes decades, suggesting that fusion propulsion is unlikely to be available within the next 30 to 40 years. The Kuiper Belt and Oort cloud lie at even greater distances, from roughly 30 to 50 astronomical units for the main Kuiper Belt to perhaps 100,000 astronomical units for the outer Oort cloud. The Oort cloud, a vast spherical shell of icy bodies thought to be the source of long-period comets, extends so far from the Sun that it begins to merge with the space between stellar systems. Reaching the inner edge of the Oort cloud with any propulsion system considered feasible within the next century would take decades at minimum. New Horizons, the spacecraft that flew past Pluto in 2015, is traveling at about 14 kilometers per second and would reach the inner Kuiper Belt's distant edge in decades and the inner Oort cloud in thousands of years. What the outer solar system and the limits of chemical propulsion reveal is that most of our solar system, by volume and by number of interesting bodies, lies beyond the reach of crewed missions with current or near-term technology. The asteroid belt, Jupiter's moons, Saturn's rings and Titan, the ice giants and their moons, all of these destinations are technically reachable by robotic spacecraft, but effectively inaccessible to humans within timeframes that can be planned or funded today. The boundary of practical human spaceflight within the solar system, at least for the next several decades, likely extends to Mars and possibly to the moon of Mars, Phobos and Deimos, or to certain near-Earth asteroids. Anything beyond represents a challenge that requires propulsion technology not yet developed. The nearest star system beyond our Sun, Alpha Centauri at 437 light-years, represents a boundary of a fundamentally different kind from anything within the solar system. It is not merely a matter of distance, though the distance is staggering, approximately 40 trillion kilometers, or roughly 276,000 times the distance from Earth to the Sun. The challenge of reaching Alpha Centauri within a human lifetime, or even within many human generations, represents a confrontation with physics itself, a set of constraints that do not bend to engineering ingenuity the way the challenges of reaching Mars or Jupiter do. Light travels at approximately 300,000 kilometers per second. At this speed, a photon takes 4.37 years to travel from Alpha Centauri to Earth. No spacecraft carrying mass can reach this speed, as special relativity establishes that accelerating a massive object to light speed requires infinite energy. Realistic spacecraft velocities are far below this limit. The fastest human-made object ever built, the Parker Solar Probe, has reached speeds of about 635 kilometers per second at its closest approach to the Sun, using gravitational assists. Even at this extraordinary velocity, reaching Alpha Centauri would take roughly 6,300 years. To reach Alpha Centauri within a human lifetime, a spacecraft would need to travel at roughly 10% of light speed or faster, corresponding to about 30,000 kilometers per second. No current technology approaches this capability. Achieving such velocities requires propulsion systems that are either purely theoretical or represent engineering challenges of a scale that dwarfs anything yet attempted. Nuclear pulse propulsion, with its theoretical specific impulse advantage, might achieve velocities of 3 to 5% of light speed under optimistic assumptions, bringing a transit time to Alpha Centauri down to roughly 90 to 150 years, still beyond any individual human lifetime, but conceivably within a generation ship's time frame. Antimatter propulsion represents the theoretical limit of rocket-based systems. Antimatter-matter annihilation converts mass to energy with 100% efficiency, producing exhaust velocities approaching the speed of light. A spacecraft equipped with an antimatter engine could theoretically reach significant fractions of light speed with transit times to Alpha Centauri of decades rather than centuries. However, producing antimatter requires more energy than it contains. Current production rates are measured in nanograms per year, and no storage system exists for the kilograms or tons needed for a propulsion system. Antimatter propulsion remains a theoretical concept constrained by fundamental production and storage challenges that appear insurmountable with any foreseeable technology. Laser sail concepts, such as the Breakthrough Starshot initiative, propose accelerating tiny probes using ground or space-based laser arrays. By using very lightweight probes with large reflective sails, the laser provides continuous acceleration without requiring the probe to carry propellant. Probes weighing a few grams might be accelerated to 20% of light speed, reaching Alpha Centauri in about 20 years. These probes could transmit data back to Earth, providing reconnaissance of the system. However, they could not carry humans. Scaling the concept to human-carrying vessels would require laser power outputs that exceed any conceivable energy infrastructure and sails of enormous size, introducing engineering challenges that appear prohibitive. Relativistic time dilation offers a partial theoretical solution. As a spacecraft approaches light speed, time aboard it passes more slowly relative to Earth. A ship traveling at 99% of light speed would experience about 1/7 of the time that passes on Earth. At 99.9%, the ratio approaches 1 to 22. In principle, this allows travelers to reach distant stars within their lifetimes, even if thousands of years pass on Earth. But this apparent advantage comes with a profound cost. A crew that departs at near light speed arrives at their destination in a time frame thousands of years removed from the civilization that sent them. The people who built the ship are dead. The institutions that funded the mission have dissolved. The language, culture, and knowledge base of the originating civilization have transformed beyond recognition. The travelers return from their subjectively brief journey to a future from which they are utterly alienated. This temporal displacement is not a solvable problem. It is a direct consequence of the physics that makes near light speed travel possible. The faster one travels to reduce subjective journey time, the greater the gulf between the traveler's clock and the civilization's calendar. At the extreme velocities needed to traverse galactic distances within a human lifetime, entire civilizations would rise and fall while the traveler was in transit. The concept of an interstellar mission that maintains meaningful continuity with the society that launched it becomes incoherent above certain velocity thresholds. The interstellar medium itself presents additional obstacles at high velocities. Between the stars, space contains a thin distribution of gas, approximately 1 atom per cubic centimeter on average, and dust grains. At low velocities, this material is inconsequential. At 10% of light speed, even a grain of dust weighing a milligram carries kinetic energy equivalent to a substantial explosive. A spacecraft traveling at interstellar velocities through the interstellar medium would experience a continuous barrage of high-energy particle impacts. Each impact vaporizes material from the spacecraft's surface, erodes shielding, and generates secondary radiation that penetrates the hull. Effective shielding against relativistic impacts requires either enormous mass or novel deflection systems, both of which add complexity and mass that the rocket equation makes increasingly costly. Navigation at interstellar distances also becomes problematic. Stars move through space, and their positions shift over decades and centuries. Radiation is the invisible adversary that accompanies every kilometer of travel beyond Earth's protective magnetic field. On Earth's surface, the combination of the atmosphere and the magnetosphere reduces radiation exposure to levels that biological evolution has adapted to tolerate. In low Earth orbit, the magnetosphere still provides substantial protection, though astronauts receive doses several times higher than the general public. Beyond the magnetosphere, in interplanetary space, that protection disappears. Galactic cosmic rays, streams of high-energy particles accelerated by supernova explosions, and other violent astrophysical events across the galaxy pervade the solar system and beyond. Solar particle events, sudden eruptions from the sun, can deliver intense bursts of radiation with little warning. Together, these sources define a radiation environment that has no analog in Earth experience, and that the human body is fundamentally ill-equipped to handle over extended periods. Galactic cosmic rays are the more persistent threat. They consist primarily of protons and heavier atomic nuclei, accelerated to energies of millions to billions of electron volts, and they arrive from all directions continuously. Their flux is relatively constant, modulated only by the solar cycle, with slightly higher intensities during solar minimum when the sun's magnetic field is weaker and provides less deflection. At the energies typical of galactic cosmic rays, these particles penetrate virtually any practical shielding, passing through the walls of spacecraft, through the bodies of crew members, and out the other side, depositing energy along their paths through ionization and nuclear interactions. The biological consequences of this energy deposition are cumulative and multi-system. When a high-energy particle passes through a DNA molecule, it can break chemical bonds, creating strand breaks that the cell's repair machinery must fix. Most damage is repaired successfully, but a fraction leads to mutations that can cause cancer decades later, or cell death that reduces the functionality of tissues. The central nervous system is particularly vulnerable. Heavy nuclei in cosmic rays, such as iron ions, have been shown in animal studies to produce cognitive deficits, memory impairment, and changes in behavior after exposures relevant to deep space missions. These effects occur through a combination of direct ionization damage to neurons and indirect effects on supporting cells and blood-brain barrier integrity. Current NASA guidelines limit career radiation exposure for astronauts to doses that limit excess lifetime cancer mortality risk to 3%. This limit, based on epidemiological models of radiation risk, is already exceeded by some long-duration ISS crew members when accounting for their full career exposures. For a crewed Mars mission lasting 18 to 24 months, estimates suggest that the radiation dose received during transit would bring crew members close to or beyond this limit, depending on solar activity and shielding design. For missions to the outer solar system, the cumulative dose would be proportionally greater, exceeding safe limits by factors that cannot be compensated by any currently available countermeasure. Solar particle events represent the acute threat. These eruptions, associated with solar flares and coronal mass ejections, can increase radiation flux in interplanetary space by factors of tens to thousands over periods of hours to days. During a major event, an unshielded astronaut could receive a dose sufficient to cause acute radiation sickness within hours, and potentially a lethal dose within days. The probability of encountering a major solar particle event during a Mars mission, which spans more than a year in transit and surface operations, is non-negligible. Estimates vary, but the chance of experiencing at least one significant event during an 18-month Mars mission is considered high enough to demand mitigation. Shielding against solar particle events is more tractable than shielding against galactic cosmic rays, because the particles involved are lower energy and can be attenuated by reasonable amounts of material. A storm shelter within the spacecraft or habitat, surrounded by water tanks, food storage, or other hydrogen-rich materials, can reduce the dose from a solar particle event to tolerable levels. Crew members would retreat to this shelter upon detection of an incoming event. However, detecting events and providing sufficient warning time is not always possible. The fastest solar energetic particles travel at nearly the speed of light and can arrive at Mars with only minutes of warning. Slower particles arrive hours later after the initial burst, which can serve as an early warning signal, but this is not guaranteed. The biological impact of the radiation environment extends beyond cancer and neurological effects. Radiation exposure accelerates cardiovascular disease through damage to endothelial cells lining blood vessels. It can cause cataracts through lens damage. It suppresses the immune system, increasing susceptibility to infections in an environment where medical care is limited. It alters the gut microbiome, which plays a role in immune function, metabolism, and possibly cognition. The cumulative effect of these diverse impacts on crew health and performance over a multi-year mission is not fully understood because no human has yet experienced the deep space radiation environment for the durations a Mars or outer solar system mission would require. Countermeasures beyond passive shielding are being developed but remain incomplete. Pharmacological radioprotection, drugs that scavenge reactive oxygen species produced by radiation damage, or that enhance DNA repair, has been shown effective in cell cultures and animal models. Human trials of some candidates are underway, but translating laboratory findings to field application in space is a complex process. The drugs must be safe for long-term use, must not impair cognitive function needed for mission operations, and must provide significant protection across the range of radiation types and energies encountered in space. Biological adaptation offers another theoretical avenue. Some organisms tolerate extremely high radiation doses through redundant DNA repair mechanisms and protective molecules. The bacterium Deinococcus radiodurans can survive doses thousands of times higher than would kill a human, using sophisticated repair pathways that reassemble shattered DNA. Understanding these mechanisms and potentially introducing them into human cells through gene therapy or pharmacological enhancement represents a long-term research direction. However, the safety, feasibility, and ethical dimensions of genetic modification for radiation resistance are profound and unresolved. The radiation barrier does not simply limit where humans can go. It limits how long they can stay and how many missions they can undertake. An astronaut who completes a Mars mission may exhaust a significant portion of their career radiation limit, restricting future assignments. A generation ship crew exposed to deep space radiation for decades or centuries would face cumulative exposures that no biological countermeasure currently known could render safe. The radiation environment of interstellar space is not qualitatively different from interplanetary space, but the duration of exposure scales with journey time, meaning that any mission extending beyond a few years enters a regime where the biological cost becomes increasingly severe. What the radiation barrier reveals is that the limits of human space travel are not solely determined by propulsion and life support. They are written into the biology of the human body, in the sensitivity of DNA to ionizing radiation, in the vulnerability of neural tissue to high-energy particles, and in the cumulative nature of radiation damage over time. These biological facts are not negotiable in the way that engineering specifications are. They cannot be overcome by more efficient design or greater investment. They can only be mitigated, partially, through shielding, countermeasures, and possibly biological modification. Until those mitigations are substantially more effective than they are today, the radiation barrier defines a boundary that limits crewed missions to destinations reachable within a few years, and it imposes escalating risks on every additional year of deep space travel beyond that. The physical challenges of spaceflight, propulsion, radiation, life support have dominated discussions of human spaceflight limits since the beginning of the space age. They are measurable, quantifiable, and amenable to engineering solutions, at least in principle. The psychological and social challenges of long-duration spaceflight have received less attention, partly because they are harder to quantify and partly because they only become fully apparent at mission durations and distances that no human has yet experienced. What research on isolated and confined environments, analog studies in Antarctica and on submarines, and the accumulated experience of long-duration spaceflight on Mir and the ISS has revealed is that the psychological and social dimensions of extreme distance impose constraints on mission feasibility that are as real and as serious as the physical ones. The fundamental psychological challenge of deep space missions is isolation, not merely from other people, which can be partially mitigated by the crew itself, but from the entire context of human civilization. Astronauts on the ISS are in near real-time communication with Earth. They can see Earth through the cupola, a luminous, recognizable presence that anchors them psychologically to the world they came from. They know that in an emergency, a return vehicle can have them home within hours. They are resupplied regularly with fresh food, personal packages from family, and new crew members who bring news and fresh perspectives. The psychological environment of the ISS, while challenging, is supported by this network of connections. For a Mars crew, these supports erode systematically as distance increases. Communication delays that begin at 3 minutes and extend to 22 minutes prevent real-time conversation. Video calls become one-way transmissions with responses arriving tens of minutes later. Spontaneous exchanges with family and friends, a significant source of psychological support for ISS crew members, become impossible. Mission control, which provides guidance, affirmation, and a sense of institutional support, can only respond to questions and reports with a delay that lengthens the longer the mission continues. The crew is effectively on its own, psychologically as well as operationally. Research on Antarctic expeditions, submarine deployments, and other isolated and confined environments has identified a predictable trajectory of psychological response to extreme isolation. Initial phases are characterized by heightened alertness, strong motivation, and cohesion among group members. As the mission progresses and the novelty wears off, a middle phase often sees reduced morale, increased interpersonal friction, and what psychologists call the third quarter phenomenon, a drop in psychological well-being as the end of the mission comes into view but remains distant. Final phases typically show renewed motivation as the end approaches. For a Mars mission lasting 18 to 24 months, this trajectory would unfold across a time frame longer than any previous isolated human mission. The third quarter phenomenon could encompass months during which crew cohesion and individual performance are degraded. Conflicts, which are inevitable in a small group under extreme stress, could escalate without the release valve of physical separation or outside intervention. Authority conflicts, personality clashes, and differences in judgment about mission decisions could fracture crew cohesion at moments when coordinated action is critical. Leadership and governance within the crew represent underexplored challenges. On short missions with clear hierarchies and close mission control oversight, command structures are straightforward. On a multi-year Mars mission with communication delays, the crew must make consequential decisions without Earth's guidance. Who has authority to override mission plans in response to unexpected conditions? How are disagreements resolved? What happens if a crew member becomes incapacitated, either physically or mentally? These questions have no established answers, and the solutions will need to be developed and tested before a mission flies, not discovered during one. Cognitive performance is another concern. Studies of long-duration ISS crew members have shown subtle but measurable changes in cognition, including reduced processing speed and altered brain white matter, detectable through neuroimaging. These changes are thought to result from a combination of fluid shifts affecting the brain, microgravity-induced structural changes in the central nervous system, and the cognitive demands of the mission environment. The extent to which these changes affect mission-critical decision-making is uncertain, but the concern is real. On a Mars mission, where the crew must execute complex surface operations, manage emergencies, and make judgment calls without guidance, any reduction in cognitive capacity could be consequential. Sleep disruption compounds these effects. Astronauts on the ISS commonly report poor sleep quality, attributed to a combination of factors including irregular light-dark cycles, noise from life support systems, workload demands, and stress. Sleep deprivation impairs cognitive performance, mood, and immune function. For a Mars crew, the Martian day is approximately 24 hours and 37 minutes, very close to Earth's, which might ease adaptation. But the first months of transit, without an external day-night cycle, could disrupt circadian rhythms and compound the fatigue that long-duration missions typically produce. The psychological impact of specific mission events must also be considered. A medical emergency, the loss of a crew member, a major equipment failure, or an accident on the Martian surface could introduce trauma that the crew must process without access to psychological professionals. Telemedicine can provide some support, but a 22-minute communication delay transforms therapy and counseling into asynchronous message exchanges that cannot replicate the responsiveness of real-time support. The crew must include members trained in psychological first aid, and mission design must build in procedures for managing acute psychological crises. Beyond Mars, the psychological constraints become more severe. A mission to the outer solar system, lasting 5 to 10 years, would push every psychological challenge to its extreme. Communication delays of hours would make Earth contact largely symbolic rather than practically supportive. The crew would experience an isolation so complete that it has no human precedent. Selection, training, and psychological screening would need to identify individuals with not only the technical skills, but the psychological resilience, interpersonal compatibility, and cognitive stability to maintain effective function over years of confinement and isolation. No evidence base exists for selecting such individuals reliably. The social dimensions extend beyond individual psychology to the structure of the crew as a small society. A generation ship carrying a population across centuries would need governance structures, educational systems, cultural institutions, and conflict resolution mechanisms. It would face the challenge of maintaining purpose and direction across generations that had no personal connection to the mission's origin or destination. Historical analogues, isolated island communities, monastic orders, long sea voyages in the age of sail provide some insight, but none that maps cleanly onto the challenges of a ship crossing the void between stars. What the psychological and social dimensions of extreme distance reveal is that human spaceflight is not only a technological problem, it is a human problem in the fullest sense, encompassing not just the survival of individual bodies, but the sustainability of social organization, psychological health, and cognitive function under conditions of extraordinary stress and isolation. The limits imposed by psychology and sociology are not fixed in the way that physics imposes limits, but they are real, and they define boundaries of feasibility that engineering alone cannot override. A mission can have adequate propulsion and life support and still fail because its crew cannot maintain the cohesion and cognitive capacity needed to operate effectively. This dimension of spaceflight limits has been under-investigated relative to its importance, and closing that gap is among the essential steps toward extending the boundary of where humans can go. Every discussion of human spaceflight limits eventually confronts a constraint that is neither physical nor biological, but economic. Space exploration consumes enormous resources, and the missions that push the boundary of human reach consume proportionally more. The Saturn V that carried Apollo crews to the moon cost, in inflation-adjusted terms, roughly $185 million per launch, and the entire Apollo program cost approximately $25 billion in 1970s money, equivalent to over $150 billion today. The International Space Station, the most expensive structure ever built, has cost over $150 billion to construct and operate since its inception. A crewed Mars mission, by most serious estimates, would cost hundreds of billions of dollars, potentially approaching or exceeding $1 trillion when all components, including launch vehicles, spacecraft, surface systems, and mission operations, are included. These numbers are not arguments against Mars exploration, but they establish the scale of commitment required. They also reveal that the limits of human space travel are not determined solely by physics or technology. They are constrained by the willingness and capacity of human societies to allocate resources to programs whose benefits are largely scientific, strategic, and inspirational, rather than immediate and economic. The history of spaceflight is as much a history of political decisions and budget cycles as it is a history of engineering achievements. Energy requirements scale dramatically with ambition. Reaching low Earth orbit requires overcoming Earth's gravity well, which demands a specific amount of energy per kilogram of payload. The energy required to place 1 kilogram in low Earth orbit is roughly 30 to 40 megajoules, approximately equivalent to burning about 7 kilograms of chemical fuel. Placing a kilogram on the lunar surface requires several times this energy. A kilogram on the Martian surface requires tens to hundreds of times more, depending on the trajectory and systems used. These energy requirements, multiplied by the mass of everything needed for a crewed mission, produce total energy demands that strain the most optimistic projections of energy availability. The rocket equation's exponential nature means that energy requirements do not scale linearly with distance or mission complexity. Adding a few more months to a mission's duration A larger crew or more equipment multiplies the required propellant mass by factors that quickly become prohibitive. This is why serious Mars mission architectures rely on in situ resource utilization, the extraction and processing of Martian materials to produce propellant and life support consumables as an essential component rather than an optional enhancement. Without local resource utilization, the mass that must be launched from Earth for a Mars mission is simply too large to be economically feasible with any conceivable launch system. Advanced propulsion concepts, whether nuclear, fusion, or antimatter-based, require energy sources and manufacturing capabilities that do not yet exist at the required scale. A nuclear pulse propulsion system sufficient to accelerate a crewed ship to a few % of light speed would require hundreds or thousands of nuclear devices, each carefully engineered to specific parameters. The infrastructure to produce these devices represents an industrial commitment comparable to the Manhattan Project, multiplied many times. Fusion propulsion, if achievable, would require breakthroughs in plasma physics, magnetic confinement, and materials science that are measured in decades of research and development. Antimatter production at propulsion-relevant scales would require energy inputs that exceed current global energy consumption by orders of magnitude. The economic challenge is compounded by timeframes. Long-duration space missions, by their nature, commit resources across administrations, political cycles, and institutional generations. Programs that span decades face the constant risk of cancellation, restructuring, or defunding when political priorities change. The history of American human spaceflight is littered with cancelled programs, each of which consumed billions before being abandoned. The Constellation program, which aimed to return humans to the Moon and eventually send them to Mars, was cancelled after years of development and billions of expenditure. Its successor, the Space Launch System, has persisted, but has been plagued by delays and cost overruns. Sustaining the political will and institutional continuity carefully, needed because it reveals something fundamental about the relationship between life challenge that and history suggests is at least any civilization anywhere in the observable universe. International cooperation faces the same event horizon from their by sharing costs and spreading technical contributions across multiple nations. But on whatever point the economic burden becomes more manageable, and the political resilience of the program increases because no single government's change of direction can unilaterally end it. The ISS is the paradigmatic example of international space cooperation, involving 15 nations and surviving multiple political cycles and tensions between the participating countries. A crewed Mars mission on a similar international model could spread costs and provide the redundancy of commitment that a single nation's program lacks. The economics of space access are changing, however, in ways that may eventually alter the feasibility calculation. Commercial launch companies, led by SpaceX, have dramatically reduced the cost of reaching low Earth orbit through reusable rocket technology. SpaceX's Falcon 9, with its reusable first stages, has reduced launch costs to roughly $2,000 to $3,000 per kilogram to low Earth orbit, compared to $10,000 to $20,000 for the Space Shuttle. Starship, if it achieves its design goals, aims to reduce costs further, potentially to hundreds of dollars per kilogram. If these reductions extend to deep space missions, the economic barrier to Mars exploration could decrease substantially. Yet even optimistic projections suggest that the full cost of a crewed Mars program would remain in the tens to hundreds of billions of dollars, a commitment that is not trivially achievable for any single nation or company. For destinations beyond Mars, the costs would scale accordingly. A crewed mission to Jupiter would require propulsion systems, life support, radiation shielding, and mission duration capabilities that do not exist, and developing them would require investments that dwarf any previous space program. The economic constraint, combined with the technological gaps, places the outer solar system and interstellar space firmly beyond reach for any foreseeable economic framework. What the energy and economic constraints reveal is that the limits of human space travel are not purely physical, but also societal. Even if physics permitted reaching certain destinations, the resources required to do so might exceed what human civilization is willing or able to provide. This is not a permanent constraint. As economies grow, as energy technology advances, and as the cost of space access continues to fall, the economic feasibility of ambitious missions improves. But on timescales of decades rather than centuries, the economic barrier is as real and as limiting as the physical ones. The boundary of where humans can go is drawn not only by the laws of physics, but by the allocation of human effort, investment, and institutional commitment that those laws ultimately require. Beyond the physical, biological, and economic constraints that limit human spaceflight in the near term lies a boundary of a different and more absolute kind. It is not set by the state of technology or the capacity of human biology. It is set by the geometry of the universe itself, by the structure of space-time and the relentless acceleration of cosmic expansion driven by dark energy. This boundary, known as the cosmic event horizon, defines the region of the universe from which it is physically impossible to receive signals or toward which it is physically impossible to travel, regardless of how much time passes or how advanced propulsion technology becomes. It represents the final, irreducible limit on how far any entity, human or otherwise, can ever reach. The universe is expanding. Distant galaxies are not moving through space away from us, but are being carried apart by the stretching of space itself. At small scales, where gravity binds structures like solar systems, galaxies, and galaxy clusters, this expansion is negligible. At cosmological scales, measured in billions of light years, the expansion becomes dominant. The rate of expansion, described by the Hubble constant, means that for every megaparsec of distance, approximately 3.26 million light-years, a galaxy appears to recede at roughly 70 kilometers per second. At distances large enough, recession velocities exceed the speed of light, not because anything moves through space faster than light, but because the space between objects grows faster than light can traverse it. The cosmic event horizon marks the distance at which recession velocity equals light speed. Currently, this horizon lies approximately 16 billion light-years from Earth. Galaxies beyond this distance recede faster than light, and photons they emit, while traveling toward us at light speed, make insufficient progress against the expansion to ever reach us. These photons travel forever but never arrive. The galaxies that emitted them fade from view, their light stretched to infinite redshift, and they become permanently inaccessible. This is not a temporary condition. Dark energy, the mysterious component whose density appears constant or growing as the universe expands, ensures that the expansion accelerates. The event horizon does not recede, it advances. Galaxies that are currently within reach will eventually cross the horizon and become permanently unreachable. This means that the accessible universe is shrinking. The overwhelming majority of the observable universe, the 2 trillion or so galaxies that can currently be detected, will eventually be carried beyond the event horizon by accelerating expansion. Only the local group of galaxies, the gravitationally bound cluster that includes the Milky Way, Andromeda, and approximately 80 smaller galaxies, will remain permanently accessible. Beyond the local group, the accessible universe ends at a boundary defined by physics, not by the limitations of technology or the endurance of biology. For practical purposes, the local group represents a vastly larger realm than any crewed mission could realistically explore. It spans several million light-years in diameter. Crossing it at even theoretical near-light speeds would take millions of years from Earth's perspective. Yet within it, in principle, all of the member galaxies remain gravitationally bound, meaning that cosmic expansion does not prevent travel between them. The Milky Way and Andromeda are approaching each other, not receding, because their mutual gravity overcomes the expansion. Within the local group, travel is constrained by propulsion and time, not by the geometry of the expanding universe. The implications of the cosmic event horizon for human spaceflight are, in one sense, not immediately practical. No mission plan, for any conceivable near-term future, contemplates reaching destinations even close to the boundary. The most ambitious proposals reach only to Mars or the nearby stars, distances of hundreds of millions to trillions of kilometers, vanishingly small compared to the billions of light-years that separate us from the event horizon. The horizon's significance is more conceptual than operational. It defines the ultimate extent of what is in principle reachable, the outer boundary within which all possible human activity in the universe must occur. That boundary is profoundly smaller than the observable universe. When astronomers look through their telescopes at galaxies billions of light-years away, they are observing objects that are already unreachable, light from regions that the universe's expansion has sealed off from any possible human visit. The observable universe, vast as it appears, is mostly inaccessible. The reachable universe, even in principle and across all possible future time, is limited to the local group and perhaps a few nearby galaxy groups within a few tens of millions of light-years, depending on the details of dark energy's future evolution. This realization has a finality to it that distinguishes it from all other limits. The limits imposed by propulsion, radiation, or economics might eventually be overcome through technological progress. The limit imposed by the cosmic event horizon is not susceptible to technological improvement. No engine, however powerful, can accelerate a spacecraft faster than light, and no amount of faster-than-light travel, being physically impossible, can circumvent the event horizon. The universe has built a wall, not of matter or energy, but of geometry, that no civilization anywhere in the cosmos can ever cross. The structure of this constraint is worth examining carefully because it reveals something fundamental about the relationship between life and the cosmos. Any civilization, anywhere in the observable universe, faces the same event horizon from their perspective. The horizon is not centered on Earth, but on whatever point the observer occupies. A civilization in a distant galaxy looks out at their own event horizon and sees that most of the universe, including our galaxy, is beyond their reach. The universe is not merely large. It is fragmented into isolated islands of accessibility, each bounded by horizons that the acceleration of expansion makes permanent and inescapable. For humanity, this means that the ultimate scope of possible activity in the universe is the local group. Within that group, the accessible volume is further constrained by the practical limits of time, energy, and biology. The stars of the Milky Way represent the realistic maximum of any expansion that could be considered human in a meaningful sense. Beyond the Milky Way, reaching the nearest galaxies would require timescales measured in millions of years and transformations of biology and society so profound that the travelers would bear no meaningful resemblance to the civilization that launched them. The cosmic event horizon is therefore not just an abstract boundary. It is the ultimate frame within which the entire story of humanity's expansion into space must unfold. A frame that is large enough to be practically inexhaustible, but finite enough to have real edges that physics will not allow any civilization to cross. After examining each layer of constraint, from the record set by Apollo 13 to the cosmic event horizon, the question of how far humans can travel in space resolves into a set of nested answers, each defined by a different timescale and technological context. These answers are not contradictory, but complementary. They describe different aspects of the same problem, each valid within its own frame of reference. Together, they define the boundary with a precision that honest assessment requires, and that the complexity of the question demands. In the immediate present, the boundary is the Moon. Apollo 13's record of 400,171 kilometers has stood since 1970. Artemis and China's lunar program aim to restore human presence on the Moon within this decade, which would re-establish the boundary at lunar distance and begin the work of understanding what extended operations beyond Earth orbit truly require. The Moon is close enough to maintain near real-time communication, close enough for emergency return to be conceivable, and close enough for resupply missions to be feasible on reasonable timescales. It is, in the most literal sense, the beginning of beyond. Within the coming decades, assuming sustained investment and technical progress, Mars becomes the boundary, The challenges are formidable but not physically impossible. Radiation exposure can be partially mitigated. Life support can be designed to high reliability. Propulsion technology, particularly nuclear thermal systems, can reduce transit times to ranges that, while stressful, are within the physiological and psychological tolerance of carefully selected and well-supported crews. The economic cost is large, but not beyond the reach of major national programs or international consortia. A crewed Mars landing before 2050 is a realistic, if optimistic, assessment of what sustained commitment could achieve. Mars would represent the most significant expansion of the human boundary in space since Apollo, and the knowledge gained from reaching it would define the next generation of exploration planning. Beyond Mars, within the solar system, the picture becomes less clear but not hopeless. Near-Earth asteroids of specific types could be reached on missions of weeks to months with relatively modest propulsion advances. The Martian moons, Phobos and Deimos, are accessible essentially as extensions of a Mars program. Venturing to the asteroid belt or the Jupiter system would require propulsion technology beyond current chemical and near-term nuclear thermal capabilities, together with life support systems capable of sustaining crews for years, radiation shielding effective over longer exposures, and psychological support structures for crews in extreme isolation over extended periods. These missions are feasible in principle, but represent challenges that likely require the second half of this century at the earliest, under optimistic assumptions about technological progress and political commitment. The outer solar system, Saturn and beyond, lies at the edge of what could be considered reachable within any near-term technological framework. The distances, transit times, and biological costs combine into a challenge that likely requires propulsion advances, fusion, or otherwise, that are decades from realization. The Kuiper Belt and Oort cloud represent the outermost reaches of the solar system, and reaching them in any human-scale timeframe would require velocities that current physics permits in principle, but current engineering cannot produce. They remain targets for robotic exploration, pushing the frontier of knowledge, while the question of crewed access to these regions remains open in a way that admits no confident near-term answer. Interstellar space, the realm beyond the Oort cloud, and the first step toward the nearest stars, represents a boundary that is not defined by specific destinations, but by the qualitative change in what travel requires. The nearest stars are not merely farther than Neptune. They are separated from us by a void that changes the nature of the problem entirely. Every constraint, propulsion, radiation, life support, communication, navigation, compounds over the timescales involved, and the combination produces requirements that exceed any technology seriously under development. Reaching the nearest stars with human crews, rather than autonomous probes, likely requires not just engineering advances but conceptual shifts in what a mission means and what continuity between the launching civilization and the arriving one can realistically be maintained. At the ultimate limit, the cosmic event horizon defines the absolute boundary that no civilization anywhere in the universe can cross. The observable universe, containing trillions of galaxies across tens of billions of light-years, is mostly permanently inaccessible. The accelerating expansion of the universe, driven by dark energy, ensures that the reachable zone shrinks over cosmic time, not grows. The local group of galaxies represents the ultimate domain within which human or any civilization's activity must be confined. Within the local group, the Milky Way's 200 to 400 billion stars, distributed across a disk 100,000 light-years in diameter, provide an effectively inexhaustible field of exploration for any civilization capable of interstellar travel. But that travel requires transformations of technology and biology that are not yet visible on any realistic development timeline. The honest answer to the question of how far humans can travel in space is therefore not a single number, but a layered assessment. Right now, 400,171 kilometers. Within decades, potentially, 54 to 400 million kilometers to Mars. Within centuries, possibly, billions to tens of billions of kilometers across the solar system. Within millennia, perhaps, the nearest stars, measured in light years, if propulsion and biology both advance sufficiently. Within millions of years, the Milky Way, if the civilization persists and transforms itself in the necessary ways. Within billions of years, the local group, if dark energy's acceleration does not change, and if civilizations can survive long enough to exploit the available time. And forever beyond reach, the vast majority of the observable universe, carried away by expansion that physics will not reverse. These layers of answer are not merely academic. They define the scope of what is worth planning, what is worth investing in, and what aspirations are physically grounded versus permanently fantastical. The boundary is real, and it is layered, and understanding it clearly is the precondition for expanding it. The history of exploration is the history of boundaries being pushed by the combination of ambition, technology, and realistic assessment of what is possible. The current limit of human space travel is modest, a single distance record set in a crisis over half a century ago, and the path beyond it is long and difficult. But it is not without direction, and the constraints that define it, physical, biological, economic, and cosmological, are well enough understood to guide the work of extending it, one layer at a time, for as long as civilization endures.